So as I said, I'm going to start again. It's only one slide or so. So as we said earlier, Introduction to Machine Learning. This is our first lectures, chapter 1. And our main objective is to go through the syllabus and the course logistic. We already done that. And also go through what is machine learning, why machine learning is important, and also types of machine learning, machine learning applications and challenges in machine learning. As we mentioned earlier, again, challenges in machine learning will be about data. Mostly we'll be concentrating more. For example, underfitting, overfitting, imbalance of training. Mostly in classification, we do a lot of evaluation also. So the evaluation issues will be more challenging for us. And as we said, types of machine learning, we'll go to supervised, unsupervised, and reinforcement. And we mention machine learning applications almost in every professional field, from banking to retail, to engineering, to medicine, everywhere, machine learning application. The main reason, as we said earlier, because of data. We have patched it. Also, the concept of big data, we may discuss that later on. We will not go through data about big data, but just the theory, a little bit of the definitely. Like, we know in big data, mostly data that are very large, and we cannot use our traditional computation ideas. So maybe distributed system, Hadoop. And also, I think the characteristics of big data, we say the 3 Vs: the volume, variety, velocity, the faster generating the data. We'll discuss that later on. So here we reach here and we talk about two different other traditional program, or here we say traditional computer science. We can write a program to do any task. But in traditional computer science, normally the program that we write, we explicitly write the instruction. So example is if I want to write a program to find the volume of, let's say, a rectangle, or let's say again, to find the gross pay of an employee. So the first thing we need is we know the employee rate, hourly rate, and the number of hours he work. And also, when there's a known formula, we know there's a formula that we can use to find the gross pay, which will be the hourly rate times the number of hours the employee. So this will not be a machine learning problem because there's a knowledge we have the known formula or the steps to solve the problem. Now with machine learning, we don't know. We know what we want as an output, and we have data, but now we want to generate some model or some, I'll say a model, a program that will make it possible to get, because in this case, we don't have for example, we want to predict whether a patient have disease A or B, and there's no formula for that. But luckily, we have some algorithm, this case, machine learning algorithms, that can help us if we give him data. We give him data will be experience. In Tom Mitchell definition of machine learning, he said we need 3 things: performance, the task, and experience. The task in this case will be, I want to know if the patient have disease A or not. The experience will come from the data. I have 10,000 patients that have that disease, and another 10,000 patients, they don't have the disease. So we give this data to the machine learning algorithm experience, going through each one, as time goes on, you get perfect on it. And also, so that is the performance at the end, let's say 80% correctly classified. Or if it's a chess, and you win or you lose. So that's the whole thing. I think the next slides will give us what we are saying here in diagram. So a traditional program, we have data. We have to write the program, the instruction, the algorithm. I want to find, again, the net pay or gross pay of an employee. I write the program, the formula with the data hourly rate and the number of hours work, and I will get the output, the gross pay. Now, with machine learning, we still have the data, but we know what we are looking for. I won't say we are looking for hourly rate. Let's say again, we are looking for prediction of a stock price or something. We have thousands of data about different stock prices and the time. So this can get an idea of time series. Yeah. So we have to choose some algorithm. That will be the program that can help us to, again, achieve our goal. So that's the whole, again, the idea here. I'm going to wait for a few seconds if any question. So normally in traditional program, human being, or I'll say human being, no, let's say the programmer is a human being. The programmer explicitly write a set of rules and also instructions that the computer must follow in order to achieve the outputs based on the diagram, achieve the output. And normally, I can also say that the output always will be predictable. So based on the number of hours you work and your hourly rate, I know your gross pay. If I give you the same number of hours and your rate, the output should be the same. So it's predictable output. And also, I would say it's manually updated. I mean, you do everything yourself. Any changes in the input to so traditional program normally, as we said earlier, is good for a no knowledge. Let's say payroll, we know how to do it. Find the area of a circle, the distance, if we know the formula here. Then the second one, as we say, we learn from data, machine learning. Yeah. So instead of we explicitly program, no, sorry, I say we, instead of the programmer explicitly programming machine learning models, we created, we learn the patterns from the game data and also if there's any relationship, etc. So that's all I can say here, if no question. As I said earlier, I'm right now on the slideshow. So if you have a question, I cannot see. If you raise your hand or you use the test, I cannot see. So you have to speak. Okay, so this is another example given here. And this is the example, it's a pattern recognition. And we can, again, if I have a problem like this, well, I mean, we all know there's no formula to use. There's no formula. So we have to create some model that will allow us, in this case, let's say, look how we write it to different persons write to, handwriting is different. So how can the machine predict or the algorithm identify if I enter two, say it's two, if it's four, five, etc. Why I'm making this example, we have this example explicitly to write a code or a program to do this is impossible. But with machine learning, yes, it's possible. It's good. We can do that. Yeah. Okay, let's move on. So next we say what is learning? That's the first thing. And according to Albert Simon, learning is any process by which a system improves performance from experience. So you can see the definition here is coming close to Tom Mitchell machine learning definition. But here we just mean general learning. So it can be a human being like me learning. If I'm learning something, I should be able to improve after I keep doing it over and over again. That's what to me. And what is the task? It can be classification, problem solving, planning, control. For example, a small baby may know this is a table. I have a table or a computer based on what they told or what he learned the first time. So next time, if they told him this is a table, next time if you see a table, nobody will tell him it's a table. So he's do this by using his brain, algorithm, so he can classify if it's a table or not, based on and also problem solving. So big data, this is the only thing we are going to say about big data. This is the only thing we are going to say. So big data is a widespread use of personal computers and wireless. So normally it's a distributed system And we take the algorithm to the data, not the data to the algorithm. Most of the time, the data cannot even go to the memory. So sometimes it's to be in the permanent storage place. One good example will be using the Hadoop environment with map, reduce, etc. Yeah. And we also have scalar, etc. Yeah. Wait for a few seconds, if no question. So the only thing I can say, big data is big. So we can say it's massive. And also, should we use the term complex, maybe complex. But as we said earlier, there's three V's, and some researchers say even up to five now. If I can remember, we have volume, and the first three is volume, variety, and velocity. So velocity means how fast we generate. Volume, the size. Variety means it can come from different source. They also added value, and there's one more V again. But earlier time it's only three V's, but I think they have up to five V's. Let's wait for a few seconds if any question. Okay, so let's keep going. So here we talk about why learning. We mentioned that, and I won't stay here too long. The only thing I'll say, the reason why I learn, first of all, even why we have machine learning today, maybe 50, 60 years ago, we don't have it. Or maybe the model, the idea is there, but we didn't. Like a good example would be neural networking. The neural networking, the first model was by McCulloch and Misk. Again, I can't pronounce it well, my accent sometimes. But it was somewhere around 1940s. I forget the actual year, but it was in the 40s. And imagine, that time, or even the way I'll put it, in the 40s, when you are designing algorithm, you design algorithm based on what? The architecture you have. Because that time, machine power, I mean the CPU, not too strong. There's no even operating system or good operating system. Storage is almost, that's why even if we can know, those of us know a little bit about programming, we can see the C language. We have Union. Actually, not C, C++. Union is a structure or like a record, a data structure. But when it comes to Java, we don't have no Union. Why? Because we know Union is good for memory management. You can use the same. But I mean, C++ say, why do we need, today we don't need memory management. If I'm designing algorithm today, I don't concern much, or we don't concern much about the machine resources. Rather, we concern about I would say the readability, how good the algorithm is, etc. So yeah, that's what I will mention here. Then also, we mentioned this earlier time. If we have to solve a problem like here again, calculate a payroll, I don't need to machine learning. I know the formula. But human expertise does not exist, like navigating on Mars, where this one, there's no knowledge. So, or speech recognition, routing on a computer network, use biometrics. So here again, machine learning concepts will come in. So to summarize everything, a very short is that when we have any complex problem, and also we don't have any no formula ways of solving it, machine learning is the best way. That's the last option. I won't say that's the last for now, but this is again, the field here is growing. This common term I forget to hear, evolution or evolve. With everyday things are happening, new things happening. So I would say that's the last option. Some other options may come. Then the next we talk about data mining. Again, in Morrow College, we have data mining class by itself. Students ask, so what's the difference between data mining and machine learning? I always say that the major difference, data mining use some of the machine learning algorithms. The major machine learning algorithm data mining uses supervised and cross story, which is part of unsupervised. Reinforcement, we don't use the data mining because in data mining we already have.
Excuse me, Professor.
Yeah,
I'm having trouble here, you know.
Or then let me ask if it's everybody. my mic is on, so there's not, unless if, can everybody hear me?
Oh, it's better now.
Okay,
Yeah.
thank you. We thank God. Oh, sorry, I should have mentioned God. Sorry. Again, I'm doing recording. Sorry. Okay, so as we said earlier, the difference between machine learning and data mining is, as I mentioned again, data mining use most of machine learning algorithms. But when you take a data mining class, you see that they focus a lot on how to prepare the data transformation, segmentation, a lot. So focus. So sometimes some textbook may say data mining is a machine learning application, even data science also. Yeah, so here we have some few examples like retail, finance, manufacturing, medicine. But the one thing I'll mention about data mining is that the data must be there. So you can't do something like that's why here we don't have the definition, but I would say data mining is how we can find knowledge in an existing large. Normally we do it in the data warehouse using machine learning algorithms such as classification, regression, clustering. Yeah. So this is just a few examples of applications for data mining. We have retail, finance, manufacturing, medicine, telecommunication, bioinformatics, and also web mining. Let's wait for, I hope everybody can hear me. Again, if you cannot hear me, especially if everybody cannot hear me, then I have to restart my computer. I hope not. But right now, I know my mic is on. I think, unless my mic go off automatically. Let me check and make sure that we continue in a second. Okay, my mic is on. Okay, now we start with the first definition of machine learning. Here we say in 1959, Otto Samuel, one of the pioneers in artificial intelligence, defined machine learning, and I highlighted it, the field of study that gives computers the ability to learn without being explicitly programmed. And I think we mentioned that earlier, the difference between machine learning and traditional programming. And also he worked on something we call the checkers play program. And to be honest here, I don't know how to play that game. I never even played before, but just we mention it here for the example. So this checkers playing program play by itself as time goes on. The more that's the getting more experience, and he improve by having a good score, etc. I will see the example. Hopefully. So this will be the fundamental definition of machine learning. Enable computers to improve their performance. And also, I would say make a prediction through experience, data. So checkers playing program, play against itself. Maybe this is a computerized system, play against itself as time goes on, more experience. So I would say in general, machine learning learn from experience, and experience, as we mentioned earlier, is the data. Yes, also we say the role of statistics and computer science. So the role of statistics is to inference from a sample. And I think one of the famous, or I would say famous, one of the main statistics algorithm, which is regression, is used again, and also probability. They are both used in machine learning. So machine learning can be, is part of statistics. In terms of computer science, how we are going to improve the algorithm. So optimization, and also representing and evaluating the model for inference. Okay, so now we go to the second and final definition, hopefully no more definition. So this is Tom Mitchell's definition, which is very famous. Most textbooks always mention it. I think our textbook also. So here they say machine learning is the study of algorithm that improve their performance P at some task T with experience E. Again, the experience is the data. The task, let's say the checkers or chess or any task, so the task will be T. And then the performance, of course, will be the measurement or the metrics. How good, if it's chess, win or lose. etc. So they say well-defined learning tasks or machine learning tasks must have these three components. So performance, tasks, and experience. And also here we say machine learning is the study of computer algorithm that automatically improve through experience. Again, the experience is the data. Wait for a few seconds if it's okay. So to repeat it one more time, as we said, experience normally will be the data, performance, how good, how the result. Let me use the term result. And T will be what I'm doing, what we are the task. Now, this is not in the textbook. I just get it from online somewhere. So, and this is from UC Berkeley. UC Berkeley normally breaks out the learning system into three main parts. So the first part is decision process. Second part, an error function. And also the last part is the model optimization process. So normally the decision process, I would say in general, machine learning algorithms, normally we use it to make a prediction or classification, etc. So I would say that based on some input data, which can be labeled or it can be unlabeled if it's unsupervised learning, our algorithm will produce an estimate or because again, one thing I'll say here is that there's no perfect. It's the same as saying programming language. We say we have thousands, not thousands, so maybe hundreds or tens of programming language, but there's no specific one perfect one. Let's say if I want to do machine learning program, I may use Python maybe instead of C++. If I want to do gaming, maybe I may use C++ instead of Python. But what I'm trying to say is that in this process, we are talking about decision process. There's no any specific. Uh, when we create a model, it's not perfect. I mean, very rare that a model will produce 100% correct classification. So here I'm just saying we can produce an estimate about the pattern of the, in this case, the pattern of the data. Let's say if it's retail, we want to estimate or predict the price of an item. But that can be like 80% accurately based on the training data set we used to build a model. So that will be the decision process. Whatever we get most of the time, it won't be again 100%, maybe to put it in that way. Now with an error function, yes, maybe some of us know about something like a gradient descent, machine neural networking, the process of learning, and also regression or residual. So what we are trying to say here that an error function normally will evaluate the prediction of the model if there are known examples. So an error function can make a comparison to again assess the comparison to assess or evaluate, let's say evaluate the accuracy of the model. And we'll go more detail, especially as we mentioned earlier, in supervised learning, yes, we do a lot of evaluations. Accuracy, total recall, ROC curve, etc. So we talk about that. And I think the last goal in computer science, we always use the term optimization. You want to get a perfect result to optimize. So if the model can fit better to the data points in the training set, let's say we are doing neural networking. The weights are normally adjusted to reduce if there's any discrepancies, error. The goal is that you want your error to be zero, or the difference between actual and predicted value to be zero. So process of adjusting. And if we can get zero, that's where optimization, we optimize the problem. So in neural network, we use the term epoch, EPOCH, every epoch. there will be adjustment. And we have a learning rate. I think they use lambda or something. It's been a while. I will go through, we'll see it in the future. So let's wait for a few seconds, if any question. Again, as I said, if you have a question, just speak. If no question, let's move on. Okay, so you have one example. I think this example we already discussed it with Tom Mitchell. Example, so here we say learning to play checkers. So in this case, our T will be, this is Tom Mitchell definition that we need at least 3 items for a good learning problem, which is TPE. So if I want to, if a system play checkers, then the task is to play checkers. Performance, how good it does. So the percent of games won. If you play the games 1,000 times, maybe you won 80% of it or 90%. And what will be the experience? The experience will be the data, but in this case, will be the more you play with its self-generating data, the more it learns. So what is the experience? What exactly should be learned? How should it be represented? And what specific algorithm to learn it? So those will be the 4 main questions we're going to ask in terms of. Okay. Now the next section is why machine learning. And why machine learning? So I won't stay too long here. We said it before. Same thing, we can say why data mining. If I have a good system, yeah, when I say system, I mean we have a good computer with a lot of memory, storage very large, CPU or even GPU can run even thousands of complex algorithm process. And also we have data variable, as we said earlier. Right now we are living a data-driven society. Then machine learning can do good job, or data mining also can do good job. So they say recent progress in algorithms and also theory. We have a lot of data, growing flood of online data. And most important is computational power. As we mentioned earlier, even neural network go all the way back to 1940s. We didn't hear anything till somewhere 1980s. I mean, we didn't hear. The real implementation was not done to somewhere 1980s, because by then our computational power is getting better. Yeah. And these are some few examples of so automated decision making, like I think recommendation on Netflix, so smart detection email, so big classification. Many years, not many, maybe 10 years or so. I don't know if they still do it. See, I should have checked. The Netflix used to have a competition every year. The best, if you can come up with the best algorithm that can do more recommendation for movies, you win $1 million. This is way back early 2000. They were doing it. They did it for many couple of years. I don't know if they're still doing it. And also recommendation system, we know Amazon are one of the first companies that uses. So also healthcare, finance, marketing, robotics, etc., etc. Machine learning can be used. Let's wait for a few seconds if it's okay. Okay. So now we go to the different types of machine learning. As we mentioned many already, we have 3 major ones here. And let's just focus on the 3 because our textbook also said 3. So we'll go through supervised learning. Supervised learning means we train a model using a label data. Actually, that's why it's called supervised. So we have what we call the training data, which have a target variable. Some application may say a class label or what we mean by target variable is that I have a data to predict a patient have disease A or B. So my training data have data that actually have the patients that the target variable disease A or B is there. So we may have A, B, or no no diagnosis. So target we know So that's, again, we'll go detail the definition self today, so we'll talk about that. Then we have reinforcement learning, and also we have unsupervised learning. So reinforcement learning, normally we learn through, actually we can see the mouse, try and error. So again, so using try and error to maximize the reward. If the mouse do a good thing, we give him a good point. If he do bad thing, we punish him, we give him lesser point. So normally the positive points will be he did better. Negative point means he did bad. And the goal is to maximize the points. Then we talk about that like policy. We have something called the value function quantity. We'll talk about that in the future. So and the last one is unsupervised. So unsupervised also opposite of supervised. We have training data, but this time we don't have no target variable. So the goal is to find some patterns in the data set. Maybe we normally use the similarity score. So we may use the distance measurement here, for example, Manhattan, Euclidean distance, Minkowski or Minkowski. Yeah, we will talk about that also. So if two things are similar, they will be in one cluster. They are not similar, they will be in different clusters. We have different algorithm. Sometimes it's based on the density, or sometimes partition, hierarchy concept, agglomerate for some. Again, the term is not coming well, but we will see it in the future slides. So we have different algorithm on that section. Here also, this is another example again for autonomous cars, which they normally use like deep learning. Reinforcement learning also is using self-driving cars also deep learning. So this was in June 2011. Nevada made it legal for self-driving cars. Self-driving. And also, when do we use machine learning? I think we mentioned it a lot, and actually this is close to what we have previously. If we have any problem and we don't have the knowledge, very complex, machine learning is very good. And that's the three summarize of the machine learning algorithms we are going to, or the categories. Let me use the term categories instead of summarize, that we are going to cover three categories. We're going to cover again the supervised learning, unsupervised learning, and also reinforcement learning. Now, we already explained just general explanation, but we'll see more detail. So first is the supervised learning. As we said earlier, learn from a labeled data. So normally we use the term training data set, training data. And so example here can be two types, regression or classification. Now, regression classification means the target variable, if it's a numerical or continuous, or it's a value, let's say a value, predicting the price of a stock or the height or weight of a person, it's a value. So that will be regression. Classification will be trying to know if a patient have disease A or B, or he tested positive or negative for COVID virus or something. Yeah, that was classified. Classification, we have two types. We can have, at least we have to have binary. You cannot say you have a classification with only one class. Let's say one type. If it's A, then everybody's A then. So either it's A and B or positive or negative, or it can be A, B, C, D, multi-class. Yeah. So example given here can be predicting a house price, so that will be regression. Email spam detection, that will be classification. And this is just a diagram to show the model. So here we have an input raw data, and this data is labeled. So we have the target variable, and this is the label here. We know this image means cow. This image means elephant. Assume. So this will be our target variable. This image is camel. And here we have all the raw data. So we put our training data into our algorithm. Let's say, look like decision tree. We do our process, and we know which are our class target for this is what we are looking for. And we were able to get them. So all the elephant will go to elephant, or the camel will go to camel. So basically, this is just the whole idea about supervised machine learning. Let's wait for a few. As I said again, you can ask questions at any time. So let's finish this section, then we take our break. Let's look at the time. Oh, it's 12:05. We need the second break now, but let's finish this section first. So as we said earlier, type of supervised learning machine, we talk about classification. We already explained it in the previous slide. The goal here, we can see our target variable span versus non-span, email, yes or no, positive. So this will be binary. And we say there are two main classification. Binary classification, which means our output will be two. Two, that's what we have here, span or non-span, email. A multiple class classification can be more than two. Let's say A, B, C, D. So we have four different classes. Class A, B, C, and D. So in machine learning, classification works by training a model, as we saw in the diagram. So how the process works, it's almost same as data mining process also. First, we get our data, collected data. Then we do our feature extraction. We get the right data we need for the model. Because now, that's why I would say data mining, we spend a lot of time. Because now, if you have a data and the data have noisy or errors, then the model you are going to create will be, there will be errors in the model. Or even if you have imbalanced data set, 90% are yes, 10% is no. It's not too good. The model will learn a lot for the yes than the no. So imbalance. So feature extraction very important. Then we model the training. Now, if we get a model, we need to evaluate it. If it's good, then we give it a test data. Then we evaluate the result we get. So normally in supervised learning, we use the training data to build a model, then we use a test data to test out. So a test data will be a data without a target variable. So now the model have to tell us if it's A or B or positive or negative. So kind of two-step method. And this is examples again for classification in real life. We talk about medical diagnosis, also image classification, sentiment analysis. This will give us the idea of a natural language processing concept, fraud detection, recommendation system, credit risk assessment, etc. Wait for a few seconds if it's okay. Okay. So here we say, let's see the key characteristics of classification model. One major is that I'll say the class separation is very, very important. I'm looking, I think we need to take a break now. So it's almost 12:10. I don't want us to take break like 12:30, then we have only 20 minutes when we come from break. So let's wait for a few seconds here if any question. Since I'm recording, actually, I need to pause this. Pause it first. So in the next section, we are going to talk about the key characteristics of classification. As I almost mentioned earlier time, class separation, I think, is very important because this is where we classify whether you are positive or negative. So class separation will rely, I would say, rely on distinguishing between the distinct classes, let's say A and B, or plus or minus. So the goal again is to learn a model that can separate, or I would say can categorize data points into predefined classes. Let's say if it's two class to a predefined plus or minus class. And based on what? Based on the features. So example we gave earlier, let's say for predicting the price of a house. Yeah, then our class, the price will be the target variable. And we want to predict the price based on what? Location of the house and the size of the house. It can be other factors, but I'm trying to use only two factors here. Actually, in the real world, sometimes we maybe have hundreds, if not tens of thousands of factors to determine one. So that's the first characteristic, classification model. The second is decision boundary. I think that's also kind of close to the idea of classification also. So the model will draw decision boundaries in the feature space. A good example would be support vector machine. We have our decision boundary. If it's 2 dimension, then a line. 3 dimension become at the three, four, fifth dimension, the image. Yeah. Wait for a few seconds. Then another example will be, yes, data sensitivity. As we said earlier, even data mining bring this issue a lot. So sensitivity to data quality. Yeah, but in supervised learning, we have some algorithms that are very good. We will use the term the robust. For example, decision tree sensitivity is an issue. Data quality is very important. But if you are using support vector machine or neural networking, especially support vector machine, because support vector machine, you may have thousands of features. The features that matters is the support vectors. That's the features that is close to the boundary. And that's the decision. Those are the one going to bring the boundary out. Again, we're going to talk about it in the future. So that's why they say support vector machine. We can have infinity dimension of data. It's used a lot in bioinformatics. Then what they do, we use the kinetic, transform it to higher definition, and as a higher definition, higher dimension, and even it can be non-linear infinity dimension. Then we transform to simple linear dimension, but in higher form, second to third, fourth dimension, fifth dimension, etc. We will talk about that. So here to me, that's what I would say. But the textbook, again, or some other book, classification is sensitive to data quality. Maybe I would say the imbalanced data can be less quality, so it can be sensitivity. But we have some algorithm that depends on the type of quality feature we are talking. Now, in terms of imbalance, it's very important. It doesn't matter whether it's support vector machine or something. So mostly we have to handle imbalanced data. And as we mentioned earlier, imbalanced data means I have 1,000 patients, 90 is positive, only 10 is negative. It's not good. We balance it. Perfect 500 positive, 500 negative. We have a training data that's balanced. Yeah. Then there are some classification algorithms. The result is very hard to understand, especially something like neural network. Decision tree interpretability is very good. Uh, if you even can go through the tree, you can even generate a rule from it. So interpretability, some classification algorithm, such as again, as I said, decision tree, give us a good higher interpretability, which means it's easy to understand. Well, what I mean, higher interpretability. Again, it's easy to understand. Compare it to neural network. Yeah. Next, we talk about the slide is not moving. Okay. We talk about the classification algorithm. Again, here we are not going to go detail, just to mention some of them here. So this is what we are going to cover for the whole. To take us like actually there's more in the next slide. It will take us like 6 to 8 weeks, and it takes. So we will learn the linear regressions, such as support vector machine is a linear. But even if you have nonlinear, it convert to linear before make decision. Now, single layer perspective transport of the neural network, but you have single layer, which means the hidden layer. Yeah, we talk about that. Like deep learning, the deep learning is a neural networking. Most textbook will tell us that deep learning is a neural network working with 5 or more hidden layers. So you can make more complex decisions. Then we also, yeah, so when we talk about gradient descent, is the time we talk about neural networking. So kind of that's the learning process. Then we have nonlinear classification also, we may discuss. Example, the k-nearest neighbor, kernel support vector machine. You see, that's why they use the term kernel support vector machine, because again, when we use the kernel concept when the data relationship is non-linear, so the kernel will convert to linear for us. We're also going to talk about naive-based decision tree. Naive is based on probability concepts. One is based on we don't care about the dependency of and one we care about it. Actually, here we don't care. So we have the as they call it, my pronunciation always. It's not here, but naive based, and when we have Bayesian or Bayesian network. Yeah, those are the two probability. Actually, most of the time I start with, again, I'll start with the learning theory first, then we go to probability concept, then we go to decision, then we move on forward. I think most of the time assembly learning classifies the one I'm going to talk last. And the one is three of them we're going to talk about. We got to talk about bargain boosting and random forest. Random forest kind of bargain too, but random forest use only decision tree. Decision trees, you use trees. That's why I call forest trees. But we can do bargain using any algorithm too. So assembly learning classifier means we create more than one model. Again, we're going to talk about it in the future. Then here we also have the multi-layer artificial neural network. So here we may have more than one more hidden layers, at least one or more. So first we talk about regression. Very quick here. Regression even take us to statistics. Normally, when we're going to do regression, we find that if there's a correlation, a simple linear regression means the dependent variable is only one. Dependent is one. When we say dependent variable, we made the features that will determine the dependent variable. Let's say a good example would be, let's say we have a company. The company annually spend over between $50,000 to $100,000 on advertisement. Let's say advertisement. And they want to know, sometimes they spend more, sometimes they spend less. Every year they spend, but sometimes some years is higher, some years is lower. So we can say, okay, we have this data set. 1990, they spent $10,000. The revenue they generate was 1 million. 1991, they spent 12,000. They generate 800,000, etc., etc. So this is our training set. Our target variable will be what? The dependent variable. How much money we are going to generate. How much revenue we're going to generate. So this will be an example of a regression, simple linear regression. First of all, we do regression statistics. We have to find out if there's a relationship between dependent and independent variable. If there's no relationship, then we don't need to do regression. If there's no association between S and Y, how can S determine Y? It cannot. Yeah, so yeah, we talk about it. Again, I won't go detail here because we're going to discuss it. Yeah, we're just going through the algorithm we are going to cover in this class. Now, types of regression. I went online a little bit and I saw so many of them. But we're going to concentrate on only three. Simple linear regression, multiple linear regression, and also logistic regression. Here, because we are dealing with the list, there's no logistic regression. Logistic regression will be nonlinear. If you want to do some work and you have to show whether it's yes or no, 0 or 1, you can do linear. So it will be like sigma, all the 1 will be on the top, all the zeros will be on the down. So if you do linear across, it won't be a good model. Mostly this kind of model would use logistic regression. Yeah. We are not going to mention about support vector regression, decision tree regression. I think decision tree regression will mention it because it's CART, C-A-R-T, classification algorithm. We have ID3, etc., C4.5, etc., etc. Yeah. Next, let's go regression. So regression evaluation metrics. Yeah, these are the possible concepts we can use. Some of us in statistics, we know what R score, I think it's called the coefficient of determination, something like that. You find the R, then score it, and that normally will tell you percentage of input that will determine the output, something like that. And normally the result is 0 to 1. If it's close to 0, then there's no good relationship there. Same as the R. R also is from 0 to 1. And if it's actually, sorry, R is from -1 to 1. Yeah, I'm going to make my first mistake. No, I'm just kidding. Let's get. So R will be from -1 to positive. Now, R squared, because it's squared, So even if it's negative 0.2, if you square it, the answer will be positive. So that's why R square values, I think coefficient determination is always 0 to 1 positive, but R is negative 1 to positive. If it's negative 1 or close to negative 1, it means when S increase, Y will decrease. When Y decrease, S increase. We have a decreasing relationship. It's close to 1, increasing relationship. If S increases, Y also increases. Again, I won't go detail on this because otherwise we can't finish what we're doing today. When we cover regression, we're going to talk. These are all ways we can measure, evaluate regression. So the applications of regression, I think we talked about some of this already, predicting prices, forecasting trend. Also, we can even identify risk, etc. Let's wait for a few seconds if any question. Okay, so if no question, let's keep going. So the next advantage and disadvantage of regression, I think I like the first one. It's one of the easy model. Easy to understand and interpret. Also robust to outliers. Outliers will be data that is extremely large or very extremely low. Yeah, extremely large or extremely low. Let's wait for a few seconds if no question. Good. So that will take us to unsupervised learning if no question. So we saw supervised learning, as we said, classification, regression. We went through some of the classification, we went through some of the regression. But we said regression is only three we are going to cover: the simple, multiple, and then logistic. So linear, non-linear. So, and also with classification, so many. Naive, support, neural network, probability concept, etc., etc. Yeah. So now let's talk about unsupervised learning. What's the difference? It's only one difference. Our target variable here doesn't exist. So we say learn from unlabeled data. So the goal is to find a pattern. The pattern here most of the time we say similarity measurement. And normally we do this based on what? Distance measurement. As I said, the most common distance will be Euclidean distance, Manhattan distance. They all use different methods. So let's see from the slide. I shouldn't go beyond myself. Learn from unlabeled data to find patterns. Example will be clustering, dimensional reduction, and then example given here, customer segmentation. So when they say market basket analysis, then that means association. This is where sometimes association can, sometimes we can use association as a classification, but most of the time association is clustering, because you want to find out if A, then B. If I buy bread, what is the chance I'll buy bread? Let's say bread, sugar. And normally in association or market basket analysis, we have two things, actually three, but two is the most important. Either we can use the confidence, not other, sorry. We have to use the confidence and also support. Then also we can find a link of something. So we'll talk about that in the future. So all this will be unsupervised learning. And some of the, see, I misplaced my slides. Okay, this slide is supposed to come before the other one. So after we finish regression, this is example for regression. So here we have example of predicting the price of a car. This is simple regression. We are using only the marriage. And we know, I think in real world also is the same thing. The more miles we have in the car, the lesser the price. So this is a decreasing relationship. So that's the model here. Data parameters modified. So we have the dot here will represent cars. So we have some cars here. And this is a training data. So we know this car, let's say this car, the marriage is 10,000. Let's say here is 10,000. And the price here, let's say this is 2,000. So this is a training data to build a model. Then we test it. And then if it's good, we put it in use. This is an example for unsupervised learning. So, okay, the reason I put the two slides, we can see the difference. with supervised learning, other regression classification, we can see that we have a training data building the model. Now, with unsupervised learning, we have data. Now we just want to find a similarity among the data. So based on here will be based on distance measurement. We were able to get 3 clusters with those 3 different colors. So that's the main goal here. So unsupervised learning in general, we say there are 3 types. Some textbook will say no, there are only one. Association is by itself, dimensional reduction is by itself. We use dimension reduction again to mostly, I would say, to reduce our. I would say now there's a difference here. When we say dimension, we don't mean we are reducing the records, but rather we are reducing the attributes dimension. Let's say I have last name, first name, year of last name, first name, date of hired, and my age. Well, and date of birth. Age and date of birth seem like they carry the same information. If the algorithm can do good and take one of them out, it's good. Now, when we are reducing record, then this is different. More or less like doing sampling. Sample, a statistic sample. Sample means I have 100 records. I want to reduce it to 50 to do my work. Dimension reduction is more complex. We have a lot of attributes. Now, if they are, so that's the dimensional case, because I forgot it. Again, pardon me for my accent. Case of dimension means you have a higher infinity dimension. Now you can see that the algorithm will take long. For example, if you are using decision tree for high dimensional data, what happens? Well, your tree will be very big, long, and then the algorithm will take long making decision going. So if a way we can cut some, they use a prune, cut some part out. But what if we do dimension reduction before we start a tree? Most likely that would do a good job. Yeah. So that's all So in this case, we say unsupervised learning is 3 branches, but it depends on what textbook you read. We can say cluster association with dimension reduction. And clustering algorithms, we may not go through all this if we have time. The major one we will go through will be the hierarchy clustering. And density based also, we may talk about that. So these are all different types of clustering. Wait for a few seconds if any question. I think the K-means will be the first one we will cover. And that's the most simple and common one because K will be the number of clusters. Means you find the center and then you find the central to do the work. Higher rank also we're going to cover. Mostly we generate the tree, building a tree step by step. They use the term dendrogram. So again, we will come to that place. Density based also we'll discuss a little bit about it. Now everything here depends on time. That's what I said earlier also in the class. If you look at the still machine learning, the algorithm, even natural language, I mean, so many applications there. Even we can say, okay, we are going to genetic algorithm, evolution, but we will not be able to cover all. So again, depends. Time is everything here. Okay, so these are some of the applications. Market segmentation, I think that makes sense. Cluster, we divided things into different sections. So market segmentation, subdivide market into based on some criteria. Here, as we said earlier, we are going to use this measurement concept. Clustering application, another one is document clustering. I want all the politics news to be one side, or politics document, sports document. So this will be based on the content. Or yeah, they say based on the term, important term that appear. Let's see another one. Okay, this will be computational biology. Genomic application group individual by genetics similarity. We know that if they perform the gene expression, if they perform, if two genes perform the same thing, they may have the same, the same function, may have the same level of expression. Cross story is good in that. Okay. So that moves us to association rule learning. So association rule learning, I think the main term we use, it will be the market basket analysis. And also the common algorithm. Here, we don't have much algorithm here. Actually, I don't know. We may have much, but we're going to cover only the apron. The idea of apron algorithm is just to reduce unnecessary rules. If they are not frequent items set, we take it out. If the top is not frequent item set, then the rest that follow below is children down may not be. So you prune again, we're going to see that. So let's see the definition. It's also known as this. It's a common technique used to discover the keyword is association. If I buy A, I also buy B. Or if A come, B will come. Or C will come next, etc. And we're only going to focus on apron algorithm of frequent pattern. This is also very common algorithm data mining textbooks. Frequent pattern growth algorithm. We also have a Hecklert algorithm. We're not going to really cover it. It depends if we have time, we will cover it. Every week I make the note, I have the note available already. So we cover, if there's some more week coming, we cover. If there's no more week, the semester is over, then we don't cover what we have to cover. So in terms of dimension reduction, only two things I know we are going to do. Principal component analysis and also singular value decomposition, which is not mentioned here, but we also have different types. Linear discriminant analysis. This reduce dimension while maximizing the class separabilities, etc. Wait for a few seconds if you have any question. Then these are some of the challenges for unsupervised learning. First is the noisy data. So noisy data, I will say the outliers or data with errors can distort, can disturb, or distort would be a good term to use, can distort again the patterns, and also can reduce the effectiveness of the algorithm. So that would be a first chance. Second, assumption dependency, also very important. Because the algorithms here often rely on, again, assumptions. What would be the assumption? I think common one we can say is the cluster, shapes, the shapes of the clusters. Overfitting issue, limited guidance, cluster interpretability, etc. Wait for a few seconds if any question. So when we say lack of ground truth, kind of a strange terminology here, but what we mean is that I would say unsupervised learning normally lag behind, lacks the label data. So there's no label data. So making it difficult to evaluate the accuracy of the result of. So we can mostly in unsupervised learning, we don't do much. We still do evaluation, but not much evaluation comparing to on the supervised learning. Okay, so let's look at the applications. So we talk about cluster segmentation, anomaly detection, normally to detect identifies unusual patterns in data. This is good for like fraud detection or cybersecurity also it's used. And also common is the equipment failure. Maybe in the production factory, based on the noise of the machine, which is not on usual noise, it to give a signal that some fault is coming or there's a fault. If we don't find it fast, it can turn to a big problem. It can break down the whole system. So anomaly detection can be used to determine this. I would say kind of like preventive maintenance, unusual noise comparing to other normal noise, always other machine noise, etc. Image and text clustering, social network analysis. Image clustering is used also in bioinformatics a lot also. Okay, so that will take us almost, we finished, almost there. Oh, got 13 minutes, that's good time. So our last session will be the reinforcement learning. As we said earlier, reinforcement learning is based on educational psychology or psychology training. I'm training a dog. If you do good, I give him a reward. If you do bad, I punish him. Because I punish him next time, hopefully he won't do the same bad again. Unless he do different bad again, the dog don't know about it. So here we say we learn by interacting with an environment. Then we receive the reward or penalty at that very. So it's kind of something happening in life, real time. So that's why reinforcement learning is not used in data mining. Self-driven car will be best. You turn to left instead of turning to right. You get punishment. And all this is generating data. So kind of experience. The data is generated. So we can even use reinforcement learning to generate a training data set, like in self-driven car. Then the training data set, now we apply deep learning on it to get a model from that. Or sometimes we can create a model direct from the reinforcement learning. Let's wait for a few seconds, see if any question. Okay, let's keep going there. So the example given here, like game playing, robotics, self-driven cars is possible. Okay. So these are some few terminology we will see or associated with reinforcement learning. Example, agent. Agent will be the decision maker that perform the action. If it's a robot or anything. Environment, that's if like a chess player, then the chessboard, the world or system which the agent operates on. So in this case, the chessboard. State, it can be in any state, or if we have more than only two states, then state positive on the so situation or condition that agent currently is in. If it's state one, then to zero, or zero back to one, it's only two state in the environment, or if it's multiple state, like a chess player, it can be different game positions, etc. Action will be what you did, what the agent did. Then you get reward will be the last section. So yeah, action will say possible move or decision that the agent can make. Then the reward will be the feedback or result from the environment based on the agent. So this will be, I would say, the framework and the terminology here. Agent will be the person making the decision, not person, but other robotic or in the agent making the decision. Environment is what we're working at. State will be what possible things we can do, how many states can change. We can change from state 1 to 2, 3, 4 based on what interaction we have. Okay, let's see. So this is the breakdown of the realm. So RL will stand for reinforcement learning component. So in the algorithm, we are going to talk about what is a policy and also what is a reward function, also value function. And also we're going to talk about the model of again, the environment, etc. Wait for a few seconds. If any question, other than that, let's move on. So as we said earlier, there's two types of reinforcement, positive and then negative. Positive is better. So we say positive maximize the performance. Negative, rather, we increase behavior frequency, ensure a minimal performance standard. Let's wait for a few seconds if no question. Again, in the future, we will go details about this. Or so, for example, we have some system, and we say the system, if you take a good action, reward will be, if positive reinforcement, reward will be +1. Negative reinforcement, reward is -1. Or 0 beginning when it hasn't started yet. So what are the applications of reinforcement learning? We say we have robotic, gameplay, industrial, control, personalizing training system, etc. In robotic, we can say normally reinforcement learning is used to automate the tasks in structured environment. Environment can be like, let's say, manufacturing environment, where the robots like Amazon have the warehouse where we have robot moving item from one stage to another, etc. So the robot learn to optimize the movement and also improve efficiency. In this case, Amazon moving product from one stage to another based on the prototype. And also gameplay and industrial control, personalized training system also. And we will discuss this again in the future. So, for example, with the personalized training system, reinforcement learning can enable the customization of instructional, let's say, instructional content based on what individual learning pattern, or even medicine, personalized medicine, maybe based on your DNA or some tests on you to give you a good treatment. So two patients may have the same disease, but because of their body content factors, let's say DNA sequence or some other factors, they may have different treatments. So each will have its own personalized treatment. So this is the advantage of reinforcement learning. We use it to solve complex problems. So reinforcement learning is, again, I would say it's capable. It's capable of solving highly complex problems that cannot be addressed by, again, normally conventional techniques. Error collection also. The model continuously learning. This is interactive, learns from its environment and can correct errors that occur during the training process or during the learning process. Again, I'm using the term learning means training process, etc. Also, direct interaction with the environment, handling non-deterministic environment. When we say deterministic environment means if you have 1, we are sure you get 10. If you get 2, we're sure you get 20. Non-deterministic, you have 1, you can get 10. Next time you have 1, you can get 20. So we cannot determine non-deterministic environment. Okay, so that will be the conclusion. Okay, let's look at the time. We've got 4 minutes. So these are the disadvantage of reinforcement learning. Not suitable for simple programs. High computational requirement, rewarding process, positive, negative, interactive, and so. But we will talk about this more in the future. Actually, this will be almost the end of the semester. We cover reinforcement learning will be the last chapter to cover. By then, we don't need it for exam. So after we take midterm, exam will be around week 9, 10. It's a very late exam. That will be the second section of the residency. After that, no more exam. But along the way, we may have short quizzes sometimes. So challenging machine learning, well, data issue. We need big data No, I don't mean big data analytics, but we need a large data. Let me use the term large, and also the quality of the data. We talk about overfitting, underfitting issues, imbalance, bias in the data, errors we need to credit solve. Result we get, interpretation should be okay. So these are some of the challenges. And that would be, okay, so the popular machine learning libraries, as we said earlier, Python is good. We get sklearn, or they also call it scikit-learn, which have most of all the machine learning packages. Pandas can be used, NumPy, Matplotlib with doing visualization with Seaborn. TensorFlow is good for deep learning, etc. So then designing a learning system. Here we said that here we assume a supervised learning. So we have training data set. Oh, recording someone there. Next time I have to do that. Okay, so we have training data set. We build our model, then we use the test set to test it, see how accurate it is. Also, data science, we said, is a new field which composed of machine learning. And also data science deal with big data analytics. So here also we do, for example, big data analytics concept comes here, like map, reduce, etc., dupe, etc. So since it's a big data analytics concept, we need a very high performance computation system, distributed system. Also data science deal with it. Actually, in general, anytime we are dealing with data, ethic and legal issue comes in. But we know privacy issues, etc. So let's hold on for a few seconds. I think this should be the last. Oh, okay, this is the last. So here, as we said, these are all the what we're going to cover in this course. So we are going to start with supervised learning, cover everything. Then we'll continue with unsupervised, then reinforcement. We also, along the way, we talk about evaluation, applications. Normally, dimension reduction, as we said, is fall under unsupervised. We're also going to cover association rule if we have time, which also fall under unsupervised learning. So our focus will be on applying machine learning to real application. And we will discuss this more when the time for discussing the final project that we talk about. As we said, this course is mostly theory. We are not using no Python, R, or anything. You can see from the syllabus also. The syllabus is departmental syllabus. So yeah, about the final project, everything, I'm not going to talk about it now. As I said, when it reaches the time, we discuss that. So hopefully next week we start with the learning theory. When we finish, then we'll continue with, I think, the decision tree or naive based probability concept, Bayesian network, etc. So let's hold on for a few seconds, if any question before we stop. Right now we have exactly, oh, that's good time, exactly 1 p.m. So let's see if we have any question. We don't have time. And then let me look. So right now I'm just going to stop the recording if no question.